Today we are going to integrate square of cos inverse of x with respect to x. So when we first look at this expression and we think of a strategy which we can use to integrate this, can we use the product rule here? No, we can't, because the derivative of cos inverse of x is not written besides it. Can we use integration by parts? No, because if we can't call this as dv over dt, because we would then have to integrate this, and we don't know how to integrate this yet. Plus, if we call 1 as u, if we call 1 as dv over dt and call this as u, then our v function will be increasing in power. If we take dv over dt as 1, v will be t square by 2, or I should say t, and the power keeps on increasing. So we can't use integration by parts here. So can we use trigonometric substitution here? Not really, because we don't have any expression which resembles the derivative of some inverse function. We don't have 1 minus x square or x square minus 1. So all of those strategies are not applicable here. So what do we do when we have a power of something which is problematic or difficult, like square of cos inverse of x? So in that kind of situation, we use substitution, normal substitution, not trigonometric substitution. And here we will substitute for cos inverse of x. So I'm calling cos inverse of x as d, and we need to replace dx in terms of t. So we need to take the derivative of t with respect to x. That becomes dt over dx is equal to minus 1 over square root of 1 minus x square, because cos inverse of x has this derivative. And we are interested in dx, so we need to separate dx from here. So dx is being divided on this side, on the other side it will be multiplied. So dt is equal to minus dx over square root of 1 minus x square. We are interested in finding the value for dx, so we'll cross multiply, and by cross multiplication we'll get minus dx is equal to square root of 1 minus x square times dt. So this negative can be shifted on the other side. So in order to find the value of dx, so dx is equal to minus times square root of 1 minus x square dt. So now we have the value for dx in terms of t. We have substituted for cos inverse of x. So this will simply become t square into the value of dx. So this will become t square times negative square root of 1 minus x square dt. Now we want to transform this whole integral in terms of t, so we don't need this x. So we need to find the value for x in terms of t, and I have moved this negative outside t square. So we know that t is equal to cos inverse of x, and we are interested in the value of x. So we need to remove this cos inverse, and in order for us to remove this cos inverse, we need to take cos of both sides. So cos of t is equal to cos of cos inverse of x, and on the right side we see that firstly we are taking cos inverse of some angle, and then we are taking cos of that answer. So essentially we are cos and cos inverse are inverse functions, so basically they cancel each other's effect. So cos t will be equal to x. So we have found the value for x, which is cos t, so we'll just put the value for x here. So minus times the integral of t square times the square root of 1 minus x square. I moved the negative sign outside, and here I have put the value for x square. So minus times the integral of t square times the square root of 1 minus cos square t dt. This becomes minus integral of t square 1 minus cos square t is equal to sine square t, because sine square theta plus cos square theta is equal to 1. Square and square root cancel each other's effect, so we are left with minus times the integral of t square sine t dt. So this is what we have, and we can see that we have a product of two functions of t. So whenever we encounter a product of two functions of t, we can think of applying integration by parts, and here it is helpful to use integration by parts because we have a function of we have a polynomial function basically here, and which is a power function, and we can use this to our advantage and can call it u, because uh, we take the derivative of u in integration by parts, and when we take the derivative of this thing, its power gets reduced, and the overall integral becomes easy for us. So we'll call this thing u and this thing dv over dt in integration by parts, because integration by parts, when we look at its definition, we have integration of u dv. So we want this thing to be in the form of u dv. We are calling this u, so this has to be dv over dt, so that dt and dt cancel out and we are left with u dv. So I'm calling t square as u and I'm calling dv over dt as minus sine t. If you observe, I have moved this negative sign inside the integral because it is easier solving that way for integration by parts, because I'm calling dv over dt as minus sine t, and for v we need to integrate this minus sine t. So the integral of minus sine t is simply cos t, because cos t has the derivative of minus sine t, and t square has a derivative of 2t, power comes in front and power gets reduced, so do 2t. So just need to use this formula. So u is basically t square, v is cos t, minus the integration of v du, this v du, v is cos t and du is simply du over dt is 2t, so du is equal to 2t dt by cross multiplication. So v is cos t and du is 2t dt. So t square cos t minus this 2 can be moved outside the integral, and we are left with the integral of t cos t dt. So again we have a product in front of us, t cos t dt, and this can be solved by integration by parts again, because this can be used as u and when we take the derivative of t, it is simply 1. So this will be much easier for us. So integrating t cos t, again using integration by parts, and using t as u here and dv over dt as cos t. So v is simply sine t and the derivative of t is 1. So applying integration by parts, so uv, which is t sine t, minus the integral of v du, so v is sine t and du is dt. So integral of sine t dt. So I'm writing this minus as plus into integral of minus sine t, because minus sine t is a known integral and it is simply the derivative of cos t. So the antiderivative of this thing will be cos t. So t sine t plus cos t, this is our value for this integral. So the solution becomes t square cos t minus 2 times t sine t plus cos t. So now we need to just simplify or rearrange these terms to get the final answer. So we have t square cos t minus 2t sine t minus 2 cos t. And remember that our integral wasn't in terms of t, we used substitution. So we need to replace all the terms involving t in terms of x. So t square is basically cos inverse x whole squared, because t was equal to cos inverse of x, and t is simply cos inverse of x. So cos inverse of x minus 2 times t is cos inverse of x, sine of t is sine of cos inverse of x, minus 2 times cos of t, so cos of cos inverse of x. Cos inverse of x whole squared remains same. Cos and cos inverse basically cancel each other's effect, so we are left with x minus 2 times cos inverse of x. This remains same. Sine of cos inverse of x minus 2x, again the same logic here, minus 2x plus c, constant of integration. And finally the solution is x times cos inverse of x squared minus 2 cos inverse of x times sine of cos inverse of x minus 2x plus c.